Welcome to our MyPath project. We are the machine learning group of the MyPath project, or you can call it the WheelShare project. Our group members are Yi Zeng, Tingzhao Wang, Bingfan Tian, Changhao Li, and Haoduan Jiang. The purpose of our project is to build an accessible routing and navigation system for wheelchair users to get to their destination from any source location. We determine accessible routes by classifying surface from vibration data. In existing mapping systems, the developers rarely consider the experience of the person with disabilities in most cases. For example, wheelchair users may encounter step slopes or other barriers in built environment, which they cannot overcome, or uneven road surfaces and broad sidewalks that are not suitable for wheeled navigation. In order to solve this problem and improve the user experience of wheelchair users, we proposed our MyPath solution. We analyzed the various factors that affect wheelchair navigation and divided them into 3 dimensions: user, wheelchair, and environment. The user dimension includes various user-related parameters, such as the user's age, height, weight, and physical capacities. And the wheelchair dimension includes the type of wheelchair, height and width of wheelchair, number of wheels, and so on. The environment dimension includes the road surface type, facilities, barriers, weather information, and so on. This project is research-oriented. The front-end and back-end works are divided across 2 capstone groups, the app development group and the machine learning group. The app group is mainly responsible for building the MyPath mobile application, which will use a smartphone embedded sensor to collect user, wheelchair, and road surface information during the navigation of a wheelchair. The machine learning team is mainly responsible for analyzing and classifying the data collected by app group and then use the machine learning models to predict any new surface data available during the testing phase of the system. The road surface information is then updated in a research-oriented open-source mapping system known as OpenStreetMap, which is a major contribution of our work. Finally, we will combine the user's personalized requirements and the accessibility of each road to generate an accessible route for wheelchair users through use a Grasshopper API, which is a dedicated routing engine for the OpenStreetMap. The biggest challenge of this project is the wide variation in user wheelchair environment combinations. It is simply impossible to collect the data from every different type of user on all possible type of wheelchairs covering all the different surfaces of the world. Therefore, we applied the 2-pronged approach to solve the problem. We use a sensor-based data collection and a path classification module for training our system on certain amount of data. From the video, you can see we are using Samsung S7 tied to the right side of the wheelchair to simultaneously collect road vibration data, and this data will be used in training our machine learning model. To create the machine learning models, we have 2 cases. The first case is the road surface which users are able to access with a wheelchair. We will use sensor data to train our machine learning model. In data collection, we use 2 kinds of sensors. One is accelerometer, and the other one is gyroscope. We represent them as surface-specific characteristic vibration patterns. We visualize the data as the graph shown. With the limitation of data as mentioned earlier, we expect to use the machine learning model to predict the surface type. Then we will determine this surface type is accessible for wheelchair users or not. We use random forest as feature extraction and then classify the data. Feature extraction and classification are separate operations in machine learning, while deep learning can merge these 2 steps together into one. So in the end, we decide to use deep learning. We use the ANN model as a classifier to predict the data.
Since our dataset for power wheelchair is smaller than the manual wheelchair dataset, we decided to use a transfer learning algorithm to empower our machine learning model for power wheelchair. When we are training our power wheelchair model, we can get knowledge from many wheelchair models by using the transfer learning to get a better performance.
To create the machine learning models, we have two cases. The first case is the road surfaces, which users are able to access with a wheelchair. We'll use the sensor data to train our machine learning model. The second case is that when users are not able to access a wheelchair. Thus, we have another approach to evaluate accessibility by using images collected for many different accessible surfaces to train the computer vision-based model. We collected images of street view, satellite, and the viewpoint on a wheelchair to train our model. Different perspectives of surfaces could help improve the classification process. Then, we label images with accessible surface polygons to identify different surfaces. Finally, we start image processing part to train the computer vision-based model.
The image labeling part is quite important because we are creating our own dataset manually so that we can train the algorithm to tell the different type of services. And the image is labeled by our categories for different type of services. And this is very important because we need to label the images as exactly as it's showing in the image so that we can ensure the accuracy. If we include the obstacle inside of the surface, the machine learning algorithm could recognize it as part of the surface, which would lead to the inaccuracy. For example, if we have a label for the concrete tail, but there are people on the concrete tail, we have to exclude them so that the algorithm will not include them as part of the surface. In addition, we use multi-level layers to help the algorithm distinguish surfaces well. This is important because it ensures the safety. If the algorithm can tell it's a sidewalk or a driving road, it could know if there is potentially people or car there, or if it's neither, it should be warn the user because you might got into the wrong way. And also, if you look at the image here, you can see we have sidewalk, driving road. It's actually the multi-level for smooth asphalt and concrete tails.
After we labeled all the images, we will have a set of the JSON file generated by LabelMe, which could be later transferred into .numpy masks for classification. First, we did some literature review on recent papers of road surface classifications and learned from the methodologies and technologies they used. After reading through around 15 papers, we attained a comprehensive view of the latest trends and ideas of surface classification technologies. Here are some of them we found useful and representative. The mainstream methodologies for image classification are pure image classification, pixel-level segmentation, and object detection-based methods. We also find some crack detection methodologies, such as binary patterns, Gabor filter, shape-based methods, and tree structure algorithms. This is a screenshot that shows how we visualize the image and its accessible surfaces. These surfaces are treated as masks in the model we used. Here, we could see the yellow masks as the rough brick surface, and the blue mask as concrete surface. Then we decide to build our model based on DeepLab v3 and ResNet 101. First, we prepare the images and masks data and set them up for training. Then, we run the training process of our model, and finally, we evaluate our predictions and model performances. Finally, we are able to cut down the loss to around 0.3 level, and we are able to add this new feature to our project.
As you can see, our task not only needs to receive and process data from the front-end, but also need to return the final routing result to the front-end. After our model feeds back road information to the OSM file, we will use these informations to provide users with appropriate navigation. Basically, the process of calculating the navigation path is like this. First, the front-end client sends a query to our server, including the coordinates of start and end point and other information. And then our server will calculate accessibility score based on various road information and user information. The road information includes the surface type and the slope of this road, and the user information including the age, height, and weight of the user. After we calculate those scores, we will assign weights to each road based on the calculated accessibility scores. And finally, we will generate 2 routes based on those assigned score and weights. In order to calculate accessibility scores, we designed the following 2 formulas. For general accessibility scores, we only consider the type of road surface and the slope of this road. For personalized accessibility scores, we also consider the user's age, height, and weight. After we calculate the accessibility score based on those 2 formulas, we will judge the comfort level of the road based on those scores, and then navigate based on these scores. Here, you can see some coefficient tables we create for different dimensions. These tables will be used to calculate the accessibility score. It includes the vibration, or you can see the surface type, the slope of the surface, and also the weight, age, height of the users. After we have the accessibility score, we can now generate the routes for the users. In order to calculate the navigation routes, we imported and modified the Grasshopper API. This API is an open source and powerful navigation API. We modified the weighting algorithm inside the API so that we can refer the accessibility score when generating the routes. And the final step of our work is to send our outcome result back to the front-end client. We use Flask framework to interact with the front-end so that the client can obtain JSON response through the URL queries. And at this point, our work is done. The outcome will transfer to the front end for the next step.
We have met lots of challenges during this senior design project. For our machine learning group, we do not have much experience in deep learning, so we spend lots of time finding the correct layers. Besides, some surveys perform very similarly in the dataset, so it is very hard to identify them precisely using machine learning algorithms. For our image classifying group, it spent a lot of time on removing those obstacles from surveys when labeling the data, and computation-based models are time-consuming to learn and implement. Current computing power is limited, so we could only perform it on low resolution. Besides, we need to communicate with the application group, so we need to prepare the Grasshopper API, and the Grasshopper API has a huge code base, making it very difficult to modify the weight calculation algorithm inside the API. We also learned a lot from this project. For example, we learned how to collaborate with other people in a long-term project, and how to report our progress clearly and periodically, like once 2 weeks or once 3 weeks, and how to effectively search for information we need from scientific resources, and how to set up small milestones during the project.